possibilities, reducing that down to 1 and 3, or 1 over.
Mm-hmm. So whenever I'm looking at a possibility, and I'll run through the question again, on a six-sided dice, or it should have said die, each side is the number between 1 and 6. So what's the probability of throwing a 3 or a 4? Those are the two events. So like I said, it's events over possibilities. All right. So you have two events, 3 or 4. That's 2. And it could possibly wind up on 1 or 6 sides. All right. So we reduce it like a fraction. You could have it one. You could say 1 in 3 chances, or you'll see 1:3.
Mm-hmm.
Means the same thing.
Okay.
All right. So let me ask you another question. What is the probability of throwing or rolling an even number?
Okay, so on the same die, rolling an even number, it would be 1 in. There's 3 possible events out of 6, so it'd be a 1 in 2.
Mm-hmm. 1 and 2. So you would see a 1 in 2 chance, or 1:2.
Yep. Okay.
All right. Good job. Good job. All right. We'll go into percentage problems. And
now, I'll show you the percentage setup. I don't. You remember how you showed the whole the voltage?
The Ohm's law triangle.
Yeah.
Mm-hmm.
So is the voltage over the current and the resistor? So you can kind of like cover one up.
Mm-hmm.
Have you ever seen the box method for percentages?
No.
Okay, so I'll just show. All right, so we'll go with 1. What percent of 29 is 3?
Mm-hmm. Now, I have a really simple way of dealing with this. It's a proportion, like you just did with your. So it's is over of equals the unknown percent over 100%.
All right, I mean, it's literally the exact same thing that I set up as far as like a box.
Mm-hmm.
So you have your part over whole, your percent over 100, and then you just cross multiply.
And that's the same thing that applies here. It's the same thing that applies here.
I've carried that with me pretty much all through life from high school. Like, it made percentages and stuff like that like extremely easy for me.
So to plug in the information, you have to watch what number follows is and what number follows of. All right.
Yeah.
So it'll be 3 over 29.
Yeah. So you're looking for the percent. So 29 is the whole. 3 is the part. So you got 29x is equal to 300. Divide by 29. Divide by 29. So, 29 into that's 81. That's 6. That's 261. 9. 81. Three. Seven. I don't know if I did something wrong on here.
Okay, let me show you how. Let me show you how to
I got
jump.
9.13.
Okay, so let me show you the speed you should be moving at. All right.
Okay.
So once you set it up, you have 3 over 29 equals our unknown percent over 100%. You're going to immediately cross multiply the 3 and the 100, which will give you 300. And I put 0.0 for accuracy. And 29 is going to go on the outside. 29 can't go into 3. 29 can go into 30 one time. 29 times 1 is 29. We subtract, we get a 1. And then the 0 drops. 29 cannot go into 10. So 29 goes into 10 0 times. All right. And we get a 0, 0, and then the second 0 drops. 29 goes into 100 3 times. All right, so it's 10.3%. So 10.3% is the answer. But you see how I just immediately just went in kind of like a shark and just get straight to the point. Because time is your worst enemy. It's your worst enemy. All right, so immediately, and the long division is not going anywhere. It's not. And you won't have a calculator. Most people hate that, but you know it is what it is.
So does all answers from across the SIFT have you found on your debriefs? Do they go to the tens place, or do they even go further?
No. 1 past the decimal point is all you really need to go.
Okay.
I take it a little bit further sometimes to the decimal point because I just want you to be very, very sure about what your answer is.
Okay.
Right.
And then obviously how far you're going to work out is indicative of the answers that you have. So if it is out to the, thousands, then obviously you're going to work out to that point.
Mm-hmm.
Okay.
So let's talk about another percentage problem. What is this number?
So that was number 1.
Let's go to number 4 because sometimes you'll have to find out what the part is.
Okay, what? So 28% from 63 is what? So 28 over 100.
Or hold on, I think I wanted us to do number 4.
Oh, I wanted to 5. Sorry.
Okay. Yeah.
Okay. Let me scratch this out real quick.
All
Okay,
right.
4. So 41% of 78.
Mm-hmm. So immediately in our is over of formula, all right. Our is unknown. Our of is 78 and 41% over 100%.
Yep.
All right. So immediately 41 times 78.
So it was 3,198.
3,198. Now the cool thing about this, check this out. 3,198. We're going to divide by 100. So guess what? The decimal point just moves over 2 spaces. Done.
Because you're cutting out the zeros.
Mm-hmm.
Okay.
So you see how quick we came up with that?
Yeah. Obviously, like when I get going, my brain starts rapid firing, and I just start immediately to process like the shortcuts and stuff like that.
Mm-hmm.
I don't pick up on until it's too late.
Mm-hmm.
So that's definitely been one thing that I've been working on, because I even started working it out in its entirety again.
So in my head, when I multiply this, and I'm going to multiply this and then move it in 2 decimal places and then done.
Okay. So if you percent of and the whole, you're just going to multiply and move 2.
Yes, sir.
Okay.
And let me see. So yeah. So sometimes they will ask you to go after different things. Alrighty. Let's see. Have we discussed kinetic and potential energy?
No.
Okay. That's something we need to talk about then. Alright. So, let's talk about kinetic and potential energy. One second here. Okay, so kinetic and potential energy, they make up total energy. And you need to understand this for the mechanical side of things.
Okay.
All right, so total energy is comprised of potential plus kinetic energy. All right. Now, in some areas, some people in physics even call this gravitational potential energy, because what you're figuring out is your gravitational potential. All right. That just went crazy. So, potential energy, the formula for potential energy is mgh, which is mass times gravity times height. All right. And kinetic energy is 1/2 mv squared. 1/2 mass times velocity squared.
Mass. Now, is that velocity?
Yes, sir.
Okay.
All right, so let me. There's a really cool question. I'll put this on the timeline. Potential energy deals with height, and kinetic energy deals with motion. All right, so in our question, we're going to address potential energy. We have a 10 kilogram ball, and it's dropped from a height of 20 meters. And we want to know what is the initial potential energy of the ball from the height at which it's dropped. So we're going to calculate potential energy. Mass times gravity times height. What is the mass, sir?
So the mass is 10 kilograms.
And what would be gravity?
Gravity, so we're dealing with a kilo, so it'd be 9.8.
Gravity is 9.8 meters per second squared. And then we have a height of 20 meters. Now, I'm going to show you how to... All right, let's say that our answer options were 2,500 joules, 1960 joules, and 1532 joules. These are our options: 2,500 joules, 1960 joules, and 1532 or 1,532 joules.
Okay.
These
The answers are off the screen.
Oh wow, sorry. Let's see here. Oh, because I'm a brain surgeon, man. All right. Hold on. Let me.
Okay.
Okay, I think we're back. Okay.
Yep.
So our answers are 2,500 joules, 1960 or 1,960 joules, and then 1532 joules. All right. Now I can solve this in 5 seconds. I'm not going to use 9.8. I'm going to use 10 because it's only going to have me 0.2 off. If my answers are spaced far enough apart, that's fine. What is 10 times 10?
100.
And what is 100 times 20?
2,000.
2,000. Which answer is the closest to 2,000?
1960.
1960. So a lot of times when you're taking a test, you can zero in the answers really quickly. Because time is our worst enemy, and we got to manipulate the hell out of it as much as we can. So the answer to this question will be 1960. All right. So potential energy deals with energy associated with height. All right. To give you another example is when we're dealing with a roller coaster and it goes over a hill. All right. Down here, let's say we have 2,000 joules of energy. It's all kinetic because we're in motion. We have to build up speed to get up that hill, don't we?
Yeah.
So kinetic energy is associated with motion. Now, as far as your total energy, it will never fall off or change. Energy can't be created or destroyed. It's either there or it's not. But it will be, for our purposes, in the form of kinetic energy or kinetic energy, or potential energy or kinetic energy. So when we get halfway up the hill, we're going to slow down a little bit, right?
Yeah.
But we'll still have kinetic energy, but we'll have 1,000 joules of potential and 1,000 joules of kinetic. Down here, we had 2,000 joules of kinetic, 0 potential, because we had no height, right? We're at the ground level. As we build height, we get more potential energy, but the kinetic energy is going to slow down. So then when we get to the top, right before, in the roller coasters where they just stop, right before they push you down the hill, at that point where we stop, we have 0 kinetic energy. We're not moving. Because you've been on a roller coaster before, how it gets to the top and it just kind of hangs there for a second. Keeps you in suspense. Yeah. All potential energy, no kinetic. Then, all right. Now what happens is, as we go down, we're slowly losing potential energy and we're gaining in potential energy. I'm sorry. We're increasing kinetic and losing potential because we're losing height or altitude. So pretty much right here is where we're going to be our fastest. But we'll be back to all kinetic, no potential. Does that make sense?
Yeah.
Okay. Just making sure. All right,
yeah,
and
pretty much like going from your kinetic into potential in this situation, you're storing all of your energy from kinetic into the potential for the apex of the roller coaster. As you tip over and gravity does its thing, then you're taking all that potential, putting it back into kinetic to continue on.
Very good. And that's exactly what's happening. Okay. Now, there is a killer question I got in the session. No, that's not the one. That's the one. Let me know when you see this question. And when you see it, I will read it aloud.
Okay.
will read it aloud. Okay. And this will help you understand the relationship between kinetic and potential and total energy. Okay, so the question reads as follows. An object with a mass of 10 kilograms is dropped from a height of 20 meters. The initial velocity of the object is 0 meters per second. Assuming the acceleration due to gravity is 9.8 meters per second squared, what would be the total amount of kinetic energy in the system when it reaches a height of 5 meters? And our answers are 50 joules, 1,050 joules, 1,471.5 joules, and 2.32 newtons. Well, we can throw the newtons out because energy is only created in joules. So that's a beautiful thing about multiple choice questions. We can root out all the garbage. Okay, and those newtons answers are garbage because we're only going to get joules. Okay, so
the newtons is force, correct?
Yes, sir. Mm-hmm.
Okay.
So now, let's think about the question. We have a 10 kilogram object. And let's say it's on a cliff. And this cliff is 20 meters high. Okay. So, I'm going to put ET for total energy is equal to E potential energy plus E kinetic energy. All right. So, first off, let's just calculate the total amount of joules in this system. And we can do that by calculating potential energy, mass times gravity times height. Now, consequently, it's pretty much like that other question. It was a 10 kilogram object in 20 meters. So, mass times gravity times height. I'm not going to use 9.8, I'm going to use 10. So 10 times 20 is 2,000 joules. Would you agree with me on that, sir?
Agreed.
Okay. So right now, this has the potential energy, or gravitational potential energy, of 2,000 joules. Okay. Now, like the roller coaster question, we saw what happened when it was halfway down. We have all our energies and potential right now. But when we get halfway down, we're going to have 1,000. Well, tell me how much potential kinetic energy you think we'll have.
Well, as soon as the kilogram, the 10K weight is dropped, it immediately goes into free fall, so there is no potential energy. It's all in kinetic because it's moving.
I would say it's building kinetic energy because the longer it takes to fall, the faster it's going to get. That is the acceleration of gravity.
Okay. So up till terminal velocity.
Right.
Okay.
So at this point, I want to know, what do you think we're going to have in kinetic and potential energy?
Okay, so it's, would it be in the halfway point that's halfway down from point A to point B?
Mm-hmm.
So it's going to be 1,000 potential, 1,000 kinetic.
Outstanding. 1,000 potential, 1,000 kinetic. Okay.
And then it'll impact the ground.
But even before
2,000.
that, let's say at 15 meters, we probably have 500 kinetic. We have 1,500 potential and 500
kinetic.
joules of kinetic. Then when we get here, we got 1,000 and 1,000. They're matched. So when we get here at the 5 meter mark, we're going to have 500 potential and about 1,500 kinetic.
Okay, so what would be the amount of kinetic energy in a system when the object reaches a height of 5 meters?
And which
so
option
the
would you take?
kinetic is 1471.5.
Right, but we didn't even have to do all that calculating because we just did our 10, and 20, which lets us know we have about 2,000 joules, and our multiple choice answers are spaced far enough apart that we could just, go with the closest to 1500, which is 1471.5 joules. So a lot of times you could just take the information, manipulate it, and make it easier for yourself. Because it's going to take much more time to say, okay, 10 times 9.8, which is 98. 98 times 20. But this still takes a multiplication. Instead of 10, 10, 100, 20, 2,000, done. It's much quicker that way. Because time is your worst enemy. It's your worst enemy. And you got to see these problems and then see them for what they are. Because if not, you're going to take too much time on one particular question.
And just out of curiosity, I do know that the math is an adaptive one.
Mm-hmm.
Have you had any guys that have stated that they've been on there for like the full 40 minutes for that portion of the test?
No, most of my guys actually they close them out early.
Okay.
Yeah, they close them out early unless they saw some really freaky questions that kind of hung them up.
Mm-hmm.
But some guys be like, no, only did 25. They got really strong scores. I think once the computer kind of is satisfied, then they're like, okay, we see where your math aptitude is. That's what it's gauging.
Yeah.
Your math aptitude. So when you really, really start getting into it and you're knocking the questions down, the computer's like, okay, let's go move on to something else. Okay.
Yeah.
All right. So that was good. Percentage problems. What else did you mention?
Just we'll do like geometry of like area and volume of like the ball shapes, not necessarily the squares or the rectangles or anything like that, but like circles and triangles and cones and spheres and stuff. Like the problem that you gave a while ago as one of those that I had to work on. I'd seen it before, and I tried to work it again without looking at my notes. It was the one that kind of looks like a ice cream cone.
Mm-hmm.
It's like a half sphere on top, or half circle on top of a cone.
Mm-hmm.
And I know what the answer is, but I've tried working it again myself, and just really can't.
Well, honestly, to be honest with you, and in my 10 plus years of preparing people for the AFAST and the SIFT, no one's ever come back with a cone and a sphere. I've heard them come back with the volume of a sphere.
Okay.
All right. Volume of a sphere. All right. And the volume of a sphere, you got to think about it. All right. The volume of a sphere is 4/3 times pi r cubed. All right. So if we're given a sphere, and let me try my best to indicate that is a sphere with a center, right? And the radius, they'll give you the radius.
Mm-hmm.
So let's say I had, I don't have anything round like a sphere. Oh, I wish I did. I got to start keeping stuff like that at my desk. But at any rate, let's say our sphere is, let's say, I don't know, 3 inches, it was like 3 inches. Let's say a really big orange with a radius of 3.
Okay.
Radius of 3 inches. Okay. What would you say the volume of that sphere is? Given that. And I'm going to work with you. Pi is 3.14.
4/3 see, pi is
3.14.
4 times 3 to the third. That's
27.
27 times 3.14 3. And that's going to be 4/3 times 0.7 over 1. That's going to reduce to 3.26. So at 30.26 over 4.
30.26 over 4?
Yeah.
I think that's off. Because your final answer should be somewhere around 113.1 units. But at any rate, let's see what I get. And this is the speed that you want to move at. 3 cubed, 3 times 3 is 9 times another 9 is 27. So 27, 3.14, 28, 9, 21, 0, 8, 2, 6. Decimal points. 8, 17, okay, 4. And then we will get 8 here. So this times this is 84.78.
That's where I messed up.
And
I had a fat finger in a 2. I ended up writing down 688 instead of 628.
Okay. So then we're going to multiply this by 4.
Okay.
32, 28. 3, 16, 18. Carry 1, 33. 339.12. If we multiply by the 4, and then we will divide by the 3. And I'll just 339 divided by 3.
This 113.
113. Okay, so that is the volume of that sphere.
I see what I had to run. I went into cross multiplication to reduce, and I just went into a whole. It's good, but okay. So 4/3 stays the same for the time being. Pi times the radius cubed. Figure that out. Multiply pi times the radius by 4, and then divide the product by 3.
Mm-hmm.
Right?
Yep. Cube, multiply by the 4, and then divide by 3.
That's actually 8. It's 84.78 times 4. Okay.
Okay, let's do. We got a couple minutes here. We have 8 minutes. Let's go into Army aviation information.
Okay.
What are 3 types of main rotor systems?
Rigid, semi-rigid, and fully articulated.
Okay. What are the differences between these 3 main rotor systems?
The rigid does not allow for like any flapping or anything of that essence. Like it's pretty much stuck. It's pinned in place.
Well, they flex. Even your rigid rotor systems, they flex, and they may be built with an aerodynamic twist in them. Like, as you go from the root or the hub of the hub, and you go out to the rotor blade tip, they may even like twist. They might be an aerodynamic twist in the blade.
Okay.
As we go from, there we go. Yeah, so as we go from the inside of the rotor outward, there could be a twist built into that rigid rotor system.
Okay.
Okay, the second one is semi-rigid. So what's that semi-rigid rotor system do? There's hinges, right? There's hinges on it, right?
Yeah, that allows for more or less flapping, right?
Lead lag. I'll recheck that.
Oh, that's right. That's horizontal movement.
Mm-hmm. And then the fully articulated does both. It lead lags,
Yeah,
and it has the teetering, and it has the flapping hinges.
So the rigid, the rigid had like that slight curve in the blade. The semi-rigid allowed for lead and lag, and then the fully articulated had both of those plus 1,000 other moving parts.
So you want to go back into your rotary wing handbook, and you want to be very, very crystal clear about that, because they may ask you weird questions. You know, they may ask you really, really, really weird questions, and you want to be crystal clear, because the wording and the multiple choice could be kind of jacked up. It might be one word, they may throw the question off, and that's why you want to be crystal clear on it. Okay. What are the major components of rotary wing aircraft?
So the major components of a rotary is the fuselage, the power plant, transmission, tail rotor, and then the main rotor hub.
Main rotor and your landing gear.
And the main rotor.
And your landing gear. Which could be skids, it could be retractable
skids or
wheels. Okay. Okay. Not bad today. There's really not much we're going to cover in 4 minutes. When are we meeting again?
I mean, we can meet kind of the same time, 6 p.m. Tomorrow, and then Tuesday is the night before the exam. So if you want to do like to do like a kind of a overall refresher, just kind of a live fire, if you will, of just random questions. And then Wednesday morning at 07:30, I have the exam at Fort Campbell.
Okay. All right. Okay. Trying to think. Monday, 6 p.m. All right. We'll talk. We'll talk. I might have an issue with my brother situation. So, but we talked about
Yeah.
that. I'll let you know. I'll let you know. But
Okay.
Wednesday morning is when you're slated to do this, right?
Yeah.
Okay. All right. I'm gonna put something together, and I will be ready for you. Okay.
Okay.
All right.
All right.
All right. All right.
All right. We'll see you later.
All right, brother. Take care.
All right. You too.
All right, ladies and gentlemen. So that was a SIFT applicant. He's testing on Wednesday. Um, yeah. If you guys have an opportunity on your social networks, please, just put in SIFT test prep or whatever. Link the video. Just tell one person. You might know somebody that wants to fly helicopters in the United States Army. This is the channel to watch. Okay, I'm going to be putting out more content. I've been really, really busy, and things are slowing down, which is good. And I'm just making sure that I put out good content for you guys. So until next time, thanks everybody for the comments and stuff like that. And for any information, just keep checking. Make sure you like and subscribe to the video, and I will talk to you guys soon. Bye-bye. Screen looks like water.